uh, Hall effect. So today we are going to see a very interesting and important phenomena called Hall effect. So for this, suppose there is a metal or a semiconductor and it is connected to a battery, and there will be a electron flow in this direction. So electrons will flow from negative charges to the positive charge side. I think hope you all know it. Now, what happens? This metal and is connected to the battery, and it is here. So now, what happens is like we will add a magnet. Okay, so we add a magnet like this near to this. So it will produce a magnetic field, right? So, and the electrons, instead of moving in the straight line like this, electrons will now try to move like this. It gets attracted a little bit to the magnet side, like magnet is pulling it. That kind of way it is moving. See, so that is the electrons are accumulating at one side, or you can say the negative charges are trying to accumulate to the one side. So what happens? The electrons trying to accumulate to the one side. So when the electrons goes to the one side, the positive charge will be here. So the negative charge is grouped here, then the positive charge will definitely be here. So the balancing happens. So, and if it so there is a potential difference. Since positive charges are here, negative charges are here, there is a kind of potential difference. And if you put a voltmeter across this, we will be able to see the measurement of that particular voltage. So this phenomenon, that is when a conductor, when it is carrying a current, that is electron flow, that is current, no? So conductor carrying a current I, when it is placed in a magnetic field, there will be an electric field induced in a direction perpendicular to both the conductors, the direction of the current and the magnetic field. So this potential difference which occurs, so this effect is known as Hall difference, and this potential difference, this voltage which is measured by this voltmeter, is called the Hall voltage. Okay, so this is the case of a conductor. Now if it is a semiconductor, so there will be electrons accumulating, and we say like there will be holes. There is absence of electrons. So if you measure it, you can feel like the same thing only. Instead of positive charge, we say it's holes. So a hole means an electron is missing. So, and it is more strong, and the Hall effect is more strong in semiconductors. So generally it is very low voltage. When we measure it by a voltmeter, we will be getting a very low voltage. So what we do is we will put an amplifier. Okay, so we will put an amplifier on, and we will measure so the amplifier amplifies the voltage. So voltage will be some higher value. So if it is a positive, the voltage is positive, then we can find like the semiconductor, this is a p-type semiconductor. Or if it is the negative, we can see like it will be a n-type semiconductor. Okay, so in conductors and semiconductors, you can see the main difference is like the electric current in conductors is mainly conducted by the free electrons. The free electrons are the main carriers. Free electrons are responsible for the electric current in conductors. But for semiconductors, it will be free electrons and holes. Okay, then we can see like this particular, whether this is a semiconductor, and if you want to increase the voltage across, the voltage developed across this after putting it in the magnetic field. So we have not shown the magnetic field here, so the magnetic field is there. So after putting them in the magnetic field, the induced voltage, the hall voltage. And if we want to increase that particular voltage, we can, if we increase the current flow. So if we are increasing the current flow, the voltage will increase. And if you are increasing the strength, the power of the magnet, if we are putting a magnet with a higher power, then also the hall voltage will increase. So more current as well as more magnetic field can increase this hall voltage. Then there is an equation for hall voltage. It is called VH. We say it is VH. So VH is equal to IB by QND. So I is the current, the electric current which is flowing through the conductor, and B is the magnetic field, the magnet which we have put, no, then magnetic field strength B, and Q is the charge. Then N is the number of mobile charge carriers per unit volume, and D is the thickness of the material, whether it is a conductor or semiconductor, the material's thickness. So we will get the hall voltage by putting the values in this particular equation. I have already told you hall voltage increases when we increases the current or when we increases the magnetic field. Okay, that is VH is directly proportional to I and B. So now see, VH is equal to IB by Q and D. So this is the equation for hall voltage. I will tell you one more thing regarding what is called the difference between mobility as drift velocity. Mobility is like, how fast an electron can move through a metal or a semiconductor. Suppose electrons, they move randomly. So in the conductor or semiconductor, they move by like one electron will touch the other electron, then the other electron will go and touch the other electron. This is usually the random movement they say. So what happens? So how fast they are moving, that is what we measure mobility. So and there is an equation for mobility also. It is Vd by E. That mobility is represented by the letter mu, and it is Vd. It is the drift velocity by E. E is the applied electric field. Sorry, the induced. It is the electric field. Okay, so mu is equal to Vd by E. I think some of you may not be aware of what is drift velocity. I'll tell you, like, so this drift velocity, which I have already told you, subatomic particles like electrons will be moving in the random directions all the time. So when an electric field is applied, they do move randomly, but they slowly drift in one direction. That is in the direction of the electric field applied. So that is so this randomly moving electrons. So when we apply electric field, it will be slowly drifting in one direction. So from random moment to, it will be like in a queue you can say. They will follow, instead of randomly moving, they will follow a queue. That is, they will be slowly drifting from one direction to another. So this net velocity in which the electrons drift, that is called the drift velocity, which is represented by this Vd. So I hope you have an idea of what Hall effect is and what mobility and what drift velocity is. One more thing I want to tell you, there's energy gap, the energy band. So there will be valence band and conduction band, you may be knowing. So the electrons in the valence band has to reach the conduction band for becoming a conductor. So the valence band and the conduction band, there will be a distance. Suppose you can simply say like there will be a height. Suppose valence band is at the ground level and conduction band's height, it will be nearer or it will be further, like that, based depending on different materials. So the electron has to jump from this valence band to the conduction band, And semiconductors, usually this gap is around zero point 0.6 electron volt to 3.4 electron volt. So when the electrons jump from this valence band to conduction band, they will be a conductor. Okay, thank you for the video. I guess hope you all can all understood. Thank you.